Welcome back, Apologia, 8th grade physical science, week 6, day 2, textbook pages 86 through 89, notebook pages 73 and 74. All right, moving along, we've been talking about the history of the atom. The last topic we discussed was Thomson's plum pudding model that Rutherford used as a basis to start his experimentation. So back in 1899, Rutherford, who was friends with Pierre and Marie Curie, was researching radioactive materials. He discovered that certain elements, such as uranium, emit fast-moving positively charged particles that he called alpha particles. He found that alpha particles could penetrate just about anything. This sparked a lot of questions for more experiments, one of which was how could he use alpha particles to learn more about the structure of an atom? All right. By 1909, Rutherford was working with two assistants, Hans Geiger and Ernest Marsden. They created a clever experiment to see what they could discover about the atom. Remember, when developing an experiment, you want to be able to accurately test your predictions. In this case, Rutherford was working from Thomson's plum pudding model of the atom. Rutherford predicted that if they sent a beam of alpha particles through a thin gold foil, that the alpha particles would go straight through. He reasoned that since the alpha particles were very fast-moving and very positively charged, they would not be affected or very minimally affected by the positively charged mass of the gold atom. This might seem counter to what you'd expect, since the positive alpha particle and the positive mass of the gold atom should repel each other. But you have to think about it the way Rutherford did, because the positive charge of the gold atom was spread out all over the whole area of the atom. The charge in any one spot of the atom would be very weak. So even though the gold atom had a positively charged mass, the charge was so weak that it would hardly deflect the speeding, highly concentrated positive charge of the alpha particles. Okay. So think about this in terms of our plum pudding or our blueberry muffin. As an example, it would be like shooting a bullet through the muffin. The muffin, which is going to resemble the atom, would hardly change the path of the bullet, which was the alpha particle. So that's where that was what he was thinking. All right. Now, Rutherford had to figure out how to observe where the alpha particles went after they hit the gold foil. This is where his clever creativity came into play. Rutherford knew that a substance called zinc sulfide would show a small flash of light when hit by scattered alpha particles. So Rutherford, Geiger, and Marsden built an apparatus similar to this. Rutherford expected the paths of the positively charged alpha particles to only be slightly affected by the gold foil they were aimed at. But more particles than expected were affected, and some bounced back at angles larger than 90 degrees. All right, so let's keep going. So Geiger, Rutherford, and Marsden built this apparatus to test their hypothesis. When Rutherford and his team began analyzing their data, they were surprised at the results. Remember, they did not expect to see any alpha particles bending too far from a straight path through the gold foil, but that was not what they found. Although most of the alpha particles did go straight through the foil, more than expected were bent off course, and some were deflected back at greater than 90 degrees from the foil. It seemed Thomson's model of the atom no longer explained all of that evidence. Their results led to more questions. What could cause a small number of the alpha particles to deflect greatly from the straight path? A few to deflect slightly, and most to go straight through as expected. Rutherford's analysis of the data from the gold foil experiment led him to formulate his own atomic model in 1911. He reasoned that the mass of the atom could not exist like the pudding in plum pudding if there were even a few deflected alpha particles. Rather, there must be a tiny but very concentrated positively charged mass. A dense mass with a concentrated positive charge located in the center of the atom would account for the result he found. He called this center mass the nucleus, and his model is often called the nuclear model of the atom. Rutherford interpreted his results based on this new model. The alpha particles that passed straight through the gold foil did not come close to a nucleus of any of the gold atoms. Those alpha particles that were slightly bent away from the straight path came close enough, but not too close to the nucleus of a gold atom so that they only slightly repelled. And those alpha particles that were bent more than 90 degrees came very close to the nucleus, and they were greatly repelled. Rutherford's model is shown here in figure 3.13. He suggested that the smaller, less mass electrons circled the positively charged nucleus, which contains most of the atom's mass, in orbits much like the planets orbit the sun. For these reasons, Rutherford's model is also called the nuclear model or the planetary model. In this model, you can see how most of the atom is empty space. Rutherford continued to research the atom and radioactivity, and in 1919, he named the positive charge in the nucleus, he called it a proton. At that time, Rutherford also suggested that the nucleus contained particles that had mass but no charge. However, it was Rutherford's student, James Chadwick, who in 1932 discovered this massive neutral particle and called it a neutron. All right, so let's just talk about this. Here we go. Go back to what Rutherford predicted using Thomson's plum pudding model. This is what he expected to happen. This is what happened and how he interpreted his results, which then made him come up with his own atomic model. The structure of an atom. You should have guessed by now that atoms are teeny, tiny, extremely small. So small, in fact, that the distance from the center of an atom to its outer edge is well under 1 nanometer, which is 1/1,000,000th of a centimeter. It may be even hard to understand just how small that is, so consider this. Inside the period at the end of a sentence would fit trillions of atoms. Thanks to the experiments of the scientists we've talked about so far, the structure of atoms is coming into focus, even without being able to see them. All right, so let's talk a little bit more about the subatomic structures or particles. Thomson, Rutherford, and Chadwick all contributed to revising Dalton's atomic theory. The evidence they collected showed that the atom was not solid and indivisible, but rather composed of subatomic particles, protons, neutrons, and electrons. But how could these tiny particles be distinguished? Well, scientists can tell protons, neutrons, and electrons apart by their mass, charge, and location in the atom. Protons, neutrons, and electrons all have different properties. Through experiments and indirect evidence, it was determined that the nucleus contained the protons and the neutrons. So here we go. We have the nucleus contains the protons and the neutrons. So again, nucleus, the center of the atom. it was determined that the electrons are very, 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 very small particles. From Thomson's experiments, it was clear that electrons have a negative electrical charge. In fact, the motion of electrons in a wire is what we call electricity. When you flip a light switch to turn on a light, for example, electrons travel through the wire to the light. The energy the electrons have in their motion is converted to light energy, and as a result, your light turns on. All right, the mass of a proton, I'm not even going to read that number, is 1,836 times more massive than that of an electron. But it's still very small. Again, it may be hard to imagine how small it is. But to picture the comparison in size, think of it this way. If the mass of a proton was the same as a 4.6 ton elephant, then the mass of the electron would be the same as a 5-pound bag of flour. Protons have a positive charge that is equal in magnitude to the negative charge of the electron. Since we know that opposite charges attract one another, we can conclude that protons and electrons are attracted to one another. Atoms are neutral because they contain the same number of protons and electrons. The neutron is roughly the same size as the proton. It is actually slightly heavier, but the difference is so small and negligible that scientists consider them to be about equal in relative mass. Neutrons are considered electrically neutral, which is where it got its name from. Scientists recognized that protons and neutrons existed in the nucleus, which accounted for the greatest part of the mass of the atom, and the tiny, tiny, tiny electrons that orbit around the nucleus. Okay, let's describe a proton. Let's just take a step back and talk about a proton. A proton is a positively charged subatomic particle. It lives in the nucleus. It's contained in the nucleus. Its mass is 1.674 times 10 to the negative 27th kilogram. And again, that's 1,836 times larger than the mass of an electron, even though, again, a proton is very small. Protons have a positive charge that is equal in magnitude to the negative charge of an electron. Protons are attracted to electrons. So that's a good starting point for understanding a proton. Let's talk about an electron. They're negatively charged subatomic particles. The mass is 9.11 times 10 to the negative 31 kilograms. And basically, they're considered nearly massless. Their weight's kind of negligible. The electrons orbit around the nucleus. Electrons in atoms exist in the spherical shells of various radii, representing the different energy levels. And again, pretty much electricity is described as the motion of electrons in a wire. All right, now let's finish up with a neutron. It has no electric charge. It's pretty much how it's got its name, neutral neutron. The mass, 1.675 times 10 to the negative 27th. It's roughly the same size as a proton, so we sort of just say it's about the same size. It's the same size. A neutron is a subatomic particle found in the nucleus of every atom, interestingly enough, though, except that of hydrogen. Let's answer some of the on your own 3.4. In Rutherford's gold foil experiment, why weren't all of the alpha particles deflected? I do want you to try to answer these in your own words. I don't mind helping explain it. But basically, okay, not all of the alpha particles were deflected in the gold foil experiment because the nucleus, it's really small compared to the whole space of an atom. So only a few of the alpha particles really came close enough to the nucleus in the gold atom to even be deflected. On your own 3.5, what three properties can be used to distinguish an electron from a proton? We've talked about this. Mass, charge, and the location in an atom can all be used to distinguish subatomic particles from each other. All right, I hope this helped.